Question 14. Two waves of the same frequency travel in opposite directions and superpose. The first wave has an amplitude of 3a, and the second wave has an amplitude of a divided by 3. These waves overlap at a point. What is the ratio of the maximum amplitude of the combined wave to the minimum amplitude of the combined wave? This question tests our understanding of superposition and interference of waves, particularly how amplitudes combine when waves overlap. What do we know? When two waves overlap at a point, the resultant displacement is found using the principle of superposition. This principle states that the displacement produced at the point where two waves meet is given by the sum of the displacement of the individual waves. For two waves of the same frequency, the maximum resultant amplitude occurs when the waves arrive in phase. In this situation, their displacements reinforce each other, producing constructive interference. The maximum possible amplitude is therefore the sum of the individual amplitudes. On the other hand, the minimum possible amplitude occurs when the waves are in antiphase. In this case, the waves oppose each other, and the resultant amplitude becomes the absolute difference between their amplitudes. Now let's think through the solution step by step. We begin by identifying the amplitudes of the two waves. The amplitude of the first wave is 3a. The amplitude of the second wave is a divided by 3. Next, we determine the maximum amplitude of the resultant wave. The maximum amplitude occurs when the waves arrive in phase, so we simply add the two amplitudes together. So the maximum amplitude equals a1 plus a2. Substituting the values gives 3a plus a divided by 3. To simplify this, we write both terms with a common denominator. 3a can be written as 9a divided by 3. So we now have 9a divided by 3 plus a divided by 3. Adding these gives 10a divided by 3, so the maximum amplitude is 10a over 3. Next, we determine the minimum amplitude. The minimum amplitude occurs when the waves are in antiphase, so we take the absolute difference between the amplitudes. So the minimum amplitude equals the magnitude of a1 minus a2. Substituting the values gives the magnitude of 3a minus a divided by 3. Again, we write 3a with the same denominator. 3a is 9a divided by 3. So we now have the magnitude of 9a divided by 3 minus a divided by 3. Subtracting gives 8a divided by 3, so the minimum amplitude is 8a over 3. Now we find the ratio of the maximum amplitude to the minimum amplitude. The ratio equals a max divided by a min. Substituting the values gives 10a over 3 divided by 8a over 3. Dividing by a fraction is the same as multiplying by its reciprocal, so this becomes 10a over 3 multiplied by 3 over 8a. The 3's cancel, and the a also cancels. This leaves 10 divided by 8. Simplifying the fraction gives 5 divided by 4, so the ratio of the maximum amplitude to the minimum amplitude is 5 to 4. This is our final answer. What did we do? We first identified the amplitudes of the two waves. Then we used the idea that the maximum amplitude occurs when the waves are in phase, so their amplitudes add together. Next, we used the idea that the minimum amplitude occurs when the waves are in antiphase, so the resultant amplitude is the absolute difference of the two amplitudes. Finally, we formed the ratio of the maximum amplitude to the minimum amplitude and simplified the result. To summarize, when waves overlap, their displacements or amplitudes add algebraically according to the principle of superposition. This is also in consideration of their phase difference, which could make any displacement a negative value. When the two waves are in phase, their amplitudes add directly to give the maximum resultant amplitude. When the waves are in antiphase, the resultant amplitude equals the magnitude of the difference between their amplitudes. And since the amplitudes in this problem are unequal, the minimum amplitude is not 0. This goes to remind us that not all destructive interference produces zero amplitudes.